Okay, let's go ahead and start. Good morning. Can you hear me okay? Yeah. So, welcome to this Monday morning. So, welcome the new participants who have not been here last week, and welcome back those who came back. I'm really happy to see that many people did come back. So, that's that's a very good thing. So, we are roughly half and half. So, roughly half people participated in the previous week, and half people uh, did not. So these 2.5 days are organized by Meena, who is sitting here. Meena, can you wave your hand? And myself. And just as in the last week, we will have several of the Northeastern students and postdocs working with us on hands-on sessions. So I see now Tsung Heng, who is here. Tsung Heng, can you wave your hand? So Tsung Heng is here. And Cyril Galitzin. Cyril, can you wave your hand as well? And I think we will have more people coming in uh, later as well. So if you are just joining us, just to tell you a little bit what we have done so far. So the first 2.5 days, we spent some time talking about working with very raw data. Well, with types of data acquisition and also working with raw data as they come out of mass spectrometer. And so we had some people working with Skyline and talking about targeted experiments, designing assays, interpreting assays, and so on. And some people worked with OpenMS and working primarily on shotgun quantitative experiments and also metabolomic experiments. And then the second half of the day, we also had two groups. And one group focused on programming with R. So this was some fairly advanced concepts on how to write your own programs and develop software with R. And the other half of the group worked on just introduction to R and also introduction to statistical methods. And so today, what we would like to do in our group is to continue on statistical methods with R, but now, unlike in the previous 2.5 days, we will focus specifically on quantitative mass spectrometry-based experiments. And so last week, we introduced, basic R and also basic statistical methods such as hypothesis testing, error bars, planning sample size, and basic plots and things like that. So this 2.5 days, we will work on kind of data specifically as they come. And so the distinctive features of these experiments are the fact that we study many proteins often, right? So it will be a very high dimensional situation. And also the fact that proteins are not measured with one peak per sample per protein, as we kind of assumed last time, right? We actually have many features, and there are all manners of difficulties, such as deviations between runs, missing values, and so these 2.5 days we will kind of work specifically on that. And so we're very excited that so not today, but tomorrow and on Wednesday, we have really good guest speakers. So we will have Rafael Irizarry, who is a prominent statistician at Harvard Medical School. He did a lot of work on normalization methods. He will give a keynote tomorrow. And then also tomorrow evening and Wednesday morning, Naomi Altman from Penn State, who is one of the co-authors of Points of Significance series in Nature Methods. She will also talk about multiple testing. And by the way, we already talked a little bit last week about the dangers associated with p-values and the statement of the American Statistical Association. There was a working group which issued the statement. So Naomi Altman was actually part of this group who developed this statement. So it will be very interesting to hear her feedback as well. But so the very first thing I would like to do, and so for the 2.5 days, most of our time, especially today completely, we will focus on detecting differentially abundant proteins. So remember last week we talked about different statistical goals. So for today, our goal is to say we have one condition, we have another condition, maybe many conditions. We want to know what is changing on average between subjects. So this is the class comparison goal. And if you were not with us last week, we will touch up on this a little bit later. But so what I would like to do, and I apologize for the redundancy, is to tell you first about the IPRG. Oh, I don't have the mouse here. Okay, we'll just have to hand wave, I guess, about the IPRG data set. So we heard about this already, but this is the data set that we will be using for hands-on exercises. And I want to make sure that those who join us right now, they know what's going on, okay? And so then we will talk about MSstats. I really wish I had some way to point. Well, okay, I guess I'll just have to point with my hand. We will talk about MSstats, and this is the software which we developed. And so Meena and Sung-Heng are the main people involved in this effort to work specifically with quantitative mass spectrometry-based experiments. And then we'll talk about some of the methods which extend MSstats. Okay, so first of all, let me just either refresh your memory or just introduce everyone to this data set. So we were involved in a study of the Association of Biomedical Resource Facilities. So this is an organization which involves people who work in core facilities. So their job is not necessarily to develop new cutting-edge methods, but rather establish good practice of quantifying protein abundances and good practice of finding differences between concentrations. And so as part of their effort, different study groups of ABRF, they make either biological samples or data sets available to their members. And so everybody goes on and analyzes these data sets using a method of their choice, and then everybody compares the results. And so in this particular study, we wanted to look at the ability of different groups to detect differences in protein abundance between conditions. But because we wanted to evaluate their performance, we had to work with a situation where we knew the answer. And so one way to do this is to create a controlled mixture where we know which proteins change in abundance and by how much. And so we did that by essentially having a mixture with a complex background. So this was a yeast lysate, which was in a tryptic digest, and these 6 proteins were spiked in this background in varying concentrations. So these are known concentrations, and so if you see here, so the first 4 proteins, they have very specific designs. So each sample contains each protein in a different concentration, and each protein appears in each sample in a different concentration. So this type of layout is called a Latin square design. And this is actually very effective because, for example, if you want to compare concentration of unit 2 and concentration of unit 15, you can do it for every protein here, 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 and here. So it means that if one particular protein was somehow negatively affected, for example, by peak overlaps or some other issues, well, you have another protein and another protein which will have the same changes. So you can actually average over multiple proteins, but at the same time, the overall amount of spiked proteins in the sample stays constant. And so this type of layout allows us to make many comparisons averaged over many proteins. And also, by the way, if you want to make this comparison, but either sample 1 or sample 2 is compromised, well, you still have the same comparison in different samples. So not only you protect yourself against some interference at the protein level, but also against potential losses in the samples. So this type of layout is well known in statistical experimental design, and so it is actually used also in genomics and so on. And so then we use that, and then we also have these 2 other proteins spiked in the background in this concentration. So in retrospect, we felt like some of these changes, like for example, these 2 are extremely large changes in concentration. They're kind of too easy. But you know, it was still a situation where we could evaluate the performance. So essentially, what we did now, we collected data. So it was a shotgun label-free experiment. So these are kind of some of the technical characteristics. The important thing is that it was label-free. Each mixture was acquired in 3 replicates. And then what we also did was, in addition to providing raw data to the participants, we could also give them results of identification of MSMS spectra. So there was some database search which were combined, and this is the number of proteins identified and so on. And in addition to the identification, we used Skyline to quantify MS1 peaks, which are mapped to these identified spectra. And so the participants could either start from the very raw data and use their own favorite pipeline, or only use the identifications and work themselves on quantification, or use ID and quant and only work on statistical side. And so the idea was for everybody to take this data, find proteins which change in abundance between conditions, and report that, but also fill in a form which summarizes different steps that they used. So what was the procedure and how they made the decisions and so on. And so this is the summary of the results. So we don't know who participated besides just some general characteristics. The study was double-blinded, so that what we actually have is only the IDs of the participants, which were anonymized. But from the form, we could kind of figure out who used what type of method. And so the first result that people had was the number of proteins which they reported. So again, complex background, right? So the just yeast background here, 6 spiked proteins. And so now the first thing is to say, okay, who reported how many proteins? So this is the study ID. So those people misunderstood the task. They only reported differentially abundant proteins. Those reported number of proteins they had in their study. These people used our identified and quantified proteins. So this is exactly the number of proteins that we had in the study. And now different color corresponds to what was their starting point. And all this group used peak intensity, this group used spectral counts, and this used some other in-house methods, and this group did not report what they used. So the very first thing, you see that the number of reported proteins varied between participants quite a bit. But this is the most important finding here. So again, the x-axis is the study ID, and the y-axis is the number of reported differentially abundant proteins over all pairs of comparisons. So it's 4 mixtures, right? So it's 4 choose 2 possible comparisons. And so above so let's say below the horizontal line is the number of reported differentially abundant proteins among the spiked proteins. So these are the true positives. And above the horizontal line, these are the reported differentially abundant proteins among the background proteins. So those are false positives. And so again, the x-axis is the study ID. The color is what type of input data they used. And the panels are if they used intensity quantification, spectral counting, or something else. And so what you can see from this is that there is a tremendous variability of the number of proteins which were reported as differentially abundant. So this group did well, right? So they primarily have true positives and very little false positives. This group did very poorly. So these guys reported 2002 differentially abundant proteins, and we only had 6 spiked proteins. So clearly there is a big difference, right? And so these studies were really useful because it allows you to kind of do some reality check, right? And say, okay, how well can we do? How consistent are we? How well do we do? So this was one thing. Then another thing was also looking for fold changes. This is the same order of study IDs as in the previous figure. The y-axis here is the absolute log to fold changes, but only among background proteins. So you kind of expect this to be very small, right? Because all the background proteins are stable. However, well, there's some noise in the spectrum, right, and some challenges with quantification. So you see that every study had some of the proteins with fairly large fold changes. And it's okay. So the important thing is that this group, they did have some background proteins which had some large fold changes, but they were not misled by that. And they could distinguish changes which were just artifacts of random variation and noise from systematic changes, and they did not report them as false positives. But this group clearly misunderstood some of these fold changes as systematic changes, and so this resulted in false positives. And so what we did next, we tried to essentially interpret the form that each participant filled, and trying to summarize different aspects. So there is the input, identification type, quantification, how multiple features of a protein were summarized, what statistical software was used, what type of models was used, adjustments for multiple testing. And so, it's really hard to see much in this besides the fact that there are many colors in this figure. And many colors means that there's a lot of ways that you can go about this problem. So you can look for differentially abundant proteins using a wide variety of methods and tools. And so it is really hard. So, the very common question people ask us about this study, okay, which software did better? Did MaxQuant do better than Skyline? And things like that. Or Perseus, did it do better than, something else? And so it turns out that it's not so easy to tell, at least from this figure. Maybe I can just point out one thing. First of all, so what we decided to do is partition them very generally into 3 groups according to their overall performance. So we quantify the performance by positive predictive value. So it's the percentage of true changes among the reported changes, right? So if somebody claims that there is a change, how likely this change is to be correct, right? And so the top group has the positive predictive value 70% or more. This one is between 20% and 70%, and this one is less than 20%. And so we think that this is good, this is not great, this is really bad. And so one thing, so even though we cannot really tell much about the colors, the only thing that I think which really comes out very clearly of that, if you look back here, the very last column is false discovery rate. And so here, I think it's not very well contrasted, but essentially the dark color means adjustments for false discovery rate, so controlling for the multiplicity of testing, and light colors meaning no control. And you see that here you primarily have light colors, and here you primarily have dark colors. So multiple testing is important. But besides that, it's really hard to tell which method maps to which performance group. And so what we also noticed is that, for example, here, people used MaxQuant and Perseus, and so some of them did very well, and some of them didn't do that well. Here, some people used Skyline and linear models in R, and so some people did well, and with the same type of tools, other people didn't do very well. Also, a common thing that people want to compare is if peak intensity performs better than spectral counts. And so here, the first group compared peak intensity with spectral counts and found that both worked well. Here, another group compared peak intensity and spectral counts and found that one was superior to the other. So clearly the conclusions differ. And so the most important message for us was this. So the same group could submit multiple answers. So it was not limited to only one method. So groups tried to use multiple methods as part of their workflow. And so here, this column highlights multiple submissions from the same group. And so what happened was that here we circle the submissions which come from the same group. And so you see that these are the submissions which were all made by some groups, and these are the submissions which were made by some other groups. And so the most important result here is that the circles don't cross this boundary. So you see that if the groups are knowledgeable, they can use multiple methods and they will do well. If the groups are less knowledgeable, they can try multiple methods and it's less successful. So this emphasizes the importance of training related to this field. So this study was published. So if you would like to learn more, it is here. So, but the reason why I'm telling you this is twofold. One is to kind of start by telling you how important it is to understand exactly what the steps are and how different choices made can really dramatically affect our performance. And the second reason is that actually for the majority of the hands-on part, we will be working with this data set. And so I wanted to make sure that those of you who just join us for the first time, you hear what this is about, because we will essentially be using different methods to look for differences between these 4 conditions. And we will see how different approaches, which kind of we have, or different steps we have to take along the way, affect the final result. So this is the idea. So any thoughts so far? Okay, so this was the repetition, but starting from now, no more repetition. So now we start new things for us. And so what I would like to do now is to tell you about the work our group did in this particular space and how we see this problem and what type of solutions we advocate. What we'll do tomorrow, we will talk about some other methods which have been developed in the context of genomics, and we will try to contrast them a little bit with what we do here so that you can have a broader perspective for that. So one of the motivating examples is this. So this was a collaboration very long time ago where our colleague was studying different cancer cell lines. So in this case, it was a low and a high invasive breast cancer cell line, so MCF7 and whatever HS578T. And she was interested not only in the cell line itself, but also in the importance of oxygen exposure. So low oxygen frequently occurs in cancer cells, especially in breast cancer. And so she was interested to see how the cell lines behave in presence of hypoxia. And so for each cell line, you also had two oxygen treatments, normal oxygen and low oxygen. And the oxygen treatment had two durations of exposure, so 6 hours or 24 hours. And then her workflow involves some enrichment and some, sample processing. So she also wanted to make sure that she accounts for the variability in these steps. So each combination of conditions, she actually had also multiple types of cell cultures and multiple types of extraction. So, and then she also had technical replicates. So quite a few layers of variation potentially in this data set. And so this would be one data set which is in this study. So here the x-axis is the combination of all the conditions. Can you see okay? I feel like it's not focused. Is it all right? I don't know how to focus this.
It might just be the fluorescent lines.
Oh. Well, I will try to explain. Maybe during the break we will see if we can do something better here. Sorry about that. Okay, so here is the condition on the x-axis, which is every combination of cell line, oxygen, and duration. So these are all the possible conditions. Now, the individual data points here, these are the replicates of this condition. And these replicates involve, the cell culture, technical replicates, and so on. And then different lines and different colors are different peptides of this protein. What I forgot to say is just the experiment was very simple, label-free shotgun LCMS experiment. And so this particular protein had 3 peptides, and so each peptide had multiple replicates here. And so we can see several things here right away. So, well, first of all, so this is the low invasive condition, this is the high invasive condition. So clearly, the protein is down-regulated in high invasive condition, right? So that's pretty simple. But now, even there, you see the different lines, they're not parallel. So each peptide is a kind of, you can think of this as a replicate, technical replicate of the same protein, right? And you would expect that all the peptides behave the same way. Well, they don't, right? So here, this particular peptide flattens out, this particular peptide goes down, and this even more. So now, the dots here, there's actually missing values, which were quantified by just some very low values in the noise region. And so the question is, well, how much does missing values affect our conclusions? And, well, this is not the whole story, because it's one thing to compare a low invasive versus high invasive cell line, but another thing is to say, well, I want to know if the difference between low and high amount of oxygen in the low invasive cell line is the same as the difference between low and high amount of oxygen in the high invasive cell line. So essentially we want to know, so this is, so we want to know how these pairs of conditions compare to these pairs of conditions. And so now the effect is much more subtle, right? So the noise between the features is quite substantial. So it's not very clear how the oxygen treatment is affected by low versus high invasive cell line. And so our goal would be, on one hand, to summarize all of these features and make sure that we can combine all the information and handle missing values and other things in an appropriate way. And at the same time, we can summarize this complex experimental design to ask questions such as, is the difference between the low in normoxin, hypoxia, low invasive cell line the same as the difference between normoxin, hypoxia, high invasive cell line? By the way, so when we just started, so what my collaborator did actually, it was very interesting. So she would literally take like a subset of runs for each comparison, and she would just analyze the subset of runs with a t-test, and then she has another comparison of interest. She would go back to the raw data, will collect a different subset of runs, and again do a t-test for a different subset of runs. And we would like to argue that we can do better than that. And by better, I mean pretty much this, right? So we can be more specific and hopefully also more sensitive than just working with pairwise t-test. Okay, so now what are the challenges? So of course, this type of behavior depends very much on the experimental workflow that you use. So for example, if you use shotgun label-free experiment, you will probably have a relatively small number of features per protein, maybe quite a few missing values and quite a few interferences or deviations between features. On the other hand, if you use data-independent acquisition, which is here, so we haven't had much chance to talk about this, but I think in the second half of this week we'll hear a lot more. So this type of experiments, they're also label-free, but you usually have quite a few more features, and they tend to have less noise than the shotgun experiments. And then you can have targeted experiments, selected reaction monitoring, which often come not only with the endogenous peptides, but also with the reference peptides. So in SRM, it's very common to spike synthetic or isotope-labeled peptides into the endogenous samples in constant concentration. And so you can kind of compare your endogenous intensities to the reference intensities. So now we have two groups of features. And so in this type of plots, the way we show this, so the x-axis is the run, the mass spectrometry run. The y-axis is the log of the peak intensity. And each line here is either a peptide ion, if it's MS1-based quantification, or a fragment ion, if it's SRM or DIE quantification. And so here, the color corresponds to the peptide sequence, and the line type corresponds to the fragment type if we have multiple fragments. So essentially, it's always some abundances which we profile between the runs, but the stochastic properties, or just the uncertainty and the variation, may depend somewhat to how we set up the experiment. And so, of course, when we do this type of analysis, it's really important that we account for the properties of the data. So that's what we set out to do. And so we developed MSstats, which is by now, I don't know how many years. I would probably say 5 to 6 years old or plus. I can't even tell. It started as a very small project which grew kind of in time. And so the goals of MSstats are as follows. So we want to work on statistical relative quantification of proteins and peptides. So class comparison, on average over replicates in group 1, is the protein changing systematically from the average of all replicates in group 2? So is this change more systematic than as expected by random chance? Or is it just consistent with random variation? And so for this, we need to synthesize all the information, understand what is our summary of the change, what is our summary of the underlying variation, and use essentially the signal-to-noise ratio approach, which we discussed last week. So what it works, kind of what it can be applicable to is any experiment with complex experimental design. So we are very happy about that. So we can work pretty much with any combination of conditions. So many conditions with cross conditions as in this cancer cell line study. So this is called the factorial experiment. And it can work with paired designs. It can work with time course. So I will probably tell you upfront that the condition is that every biological replicate has a unique identifier. It's not a very strict condition. And we kind of work from that to figure out what the experimental design is. So for the moment, MSstats is applicable for experiments with chromatography-based quantification. So where we use chromatographic peaks for quantification. So shotgun, SRM, DIA, PRM. So this works. What it doesn't work with yet is iTrack or TMT, because iTrack or TMT reporter ions do not have the chromatography profile, right? They're more like reporter ions. So these methods can be extended, but for the moment we don't have them implemented in the default. So we can work with label-free or label-based, so especially if we have synthetic labeled reference peptides. And we have multiple functionalities which kind of track all the steps of the data processing. So we visualize the data and we can do quality control and things like that. Then there is statistical modeling, model-based conclusions. And as I mentioned last week, every time we analyze a data set, we immediately think of this as a pilot study for some other follow-up experiment. So we also quantify variance components and we project a sample size required for that. And of course, it's very important to say that this is free and open source. It's all entirely implemented in R. So it is available by itself, and that's what we will practice today. So we'll be working with this within R. But there are also other opportunities. So for example, for Skyline, it is available as an external tool. So if someone is afraid of R and doesn't want to see it, you can just click and use graphical user interface from Skyline. Now, the problem is that the options available through this are more limited. So it is really better if you can use the full-blown version within R. But this is an option as well. And we try to be as inclusive as possible and work with data processing tools from many places. So our input is really tabular format, so you can use OpenMS, MaxQuant, Skyline, whatever your favorite tool is to actually get the data in this format. So we'll talk, and we have some converters for that, so I think Meena will probably comment on this quite a bit more after that. But so this is what we have as far as the data structure. So this is one protein, and this is the very general kind of representation that MSstats has kind of in mind. So it's a table, and so this is what you would get kind of out of the data processing tools. So the columns here are different runs. So the runs are grouped by condition, and the convention in MSstats is that condition is the combination of all the factors that you may have. So for example, in the cancer cell line study, one condition will be 6 hours, low oxygen, low invasive cell line. The next condition will be 24 hours, low invasive, low oxygen, right? And so essentially one condition will be all combination of all the things, all the stresses which were applied to the cell line. Now, within each condition, I will have multiple biological replicates, and each biological replicate can be represented by multiple runs, either because it's technical mass spectrometry runs, or because there were multiple sample processing enrichment steps, which resulted in different mass spectrometry runs after that. And so the important things are that each protein has many features, which may or may not behave in the same way, right? And so we quantify every peak on the log scale, and we talked about this last week, because statistically it's much easier for us to work with differences, and difference of logs is the log of the ratio, right? So we just kind of work with the log ratios, but we can do a lot more if we work with differences. And of course, the important thing is the missing values, and the missing values will be a really big part of what we have to deal with. And so this is the actual input. So this is the abstraction that we have in mind, but what you actually get inside MSstats is slightly different form. So this is a kind of statistic, it's called wide format, where you have replicates kind of like this in columns, and you just have multiple features in the rows. But what technically what we actually read into MSstats is a long format. So this is an Excel file or any other tabular file that you want. And so here, one row, one line is actually not a feature, but one line is literally a peak. So each peak is characterized by the protein name, peptide sequence, precursor charge, fragment ion. If it's a DIA or SRM experiment, it will be NA if it's a label-free experiment. precursor charge, isotope labeled, so it's either heavy or light. If it's a label-free experiment, everything is light. This is important. This is the identifier of the biological replica, and this is the run ID, and this is the actual intensity on the original scale. So if you have a protein which has 10 features, in the first run you will have 10 lines, because each feature in the run will have a separate peak, and each peak will be described with all of these things. So now if you have 10 features in a run, and you have 3 runs, you have 30 lines. So they just kind of become concatenated. And this is a very good format because it really represents many different experiment times in a very consistent way. And so, for example, Skyline external tool, what it does, it exports a report exactly in this format. So we work very closely with Skyline to generate MSstats report exactly as is. Now, MaxQuant, for example, doesn't generate a report in this format, but we have a converter which will take MaxQuant native files and essentially format the data this way. And so Meena will be able to comment more on that. Okay, but let me now tell you about the steps that we have to perform and just kind of the philosophy behind that. So the whole workflow, in a very general way, is this. And this really is not very specific to mass spectrometry or proteomics. If you have worked with genomic data sets or metabolomic data sets or anything, this is what we would do, right? And by now, I hope, if you were here last week, you know that the first thing we need to do is to design the experiment, and we need to talk to a statistician before collecting the data, right? So that's what happens here, right? So we need to make sure we know our question, right? We know how many replicates we need. We know if we want to use blocking or some other type of strategies, right? If we like how to randomize and so on. So all of this happens before collecting the data. And we really should not underappreciate that, because as we said last week, if things go wrong here, no amount of hard work here will compensate for problems. So essentially, it can be a wasted experiment at best and completely misleading and wrong conclusions at the worst, right? And irreproducible conclusions. Okay, but so once the data are collected, so this is really where MSstats works primarily, right? So it is quality control normalization, and there are actually several types of QC. I hope to touch on that at the end, and I know that Rafael Rizari will talk about this as well. We'll talk about statistical models that we develop, how we use the models to make conclusions, and then how we work on the experimental design. And so the way, so when MSstats gets an input file like that, what we actually do, we look at the IDs of biological replicates and see in which runs they're located. So if the biological replicate is present in many runs or in many, so we know that it has technical replicates. If the biological replicate is present, the same biological ID is present in many conditions, then we know that it's a time course or paired design, that the same person was measured at multiple time points. Or sometimes, for example, you have the designs where you have the tumor sample biopsy and then a healthy tissue biopsy. So then you will have a tumor and healthy condition, but both from the same biological replicate. So that's how we will know. So MSstats behind the scenes parses that, right? So this unique identifier of biological replicates help us with that. And so this is one example. So by the way, this is another example from the study that we had also a while ago. So this was a study of osteosarcoma. So these are childhood cancers, and they're fairly rare, but they're very damaging. And so our collaborators, they had 29 healthy controls and 14 disease subjects. And now for the disease subjects, they had plasma samples at diagnosis. Then they had some measurements of during chemotherapy, and then they had some measurements after chemotherapy. And I don't have space here, but they also had after remission, so sometime after they came back for a follow-up. So there's another time point much later in time here. And so here's the design. So these are different people, right? So these are two different groups. One group just has 1 point, the other group has multiple time points. And you can ask questions such as, well, is the protein abundance here differs from the protein abundance in the controls. After the treatment, did the protein abundance get reduced to the level of controls? Or did it stay the same at the level of the disease? And things like that. So this is an example of a design that you really want to analyze jointly all the conditions, but you need to know how to represent these conditions. And most importantly, how to characterize the variation associated with that. To say that this change is more systematic than just random chance. Yes?
So is there any argument for measuring also a time point for the controls? I mean, these are young children, this is in the span of some time because it will protein.
Very much so, they just couldn't have it. Because it is much easier in a sense to have patients with a disease to come back to see a doctor than kids who are healthy to come back and see a doctor. So I think it was more an artifact of sample availability than the optimal kind of situation. Very much so, of course, depending especially how long the treatment lasts. The kids grow, and some of these things indeed are associated with age and not with the disease. Very much so. So I think that's just their limitation that they had. And in fact, it's in many cases, I see that controls are much more difficult to find, the appropriate controls, right, than the disease. So imagine you are studying, I don't know, brain tumor, right, and you have tissue from the biopsy, because that's what happens when there is a surgery, right? Well, no healthy volunteer will, volunteer their brain sample, right? So oftentimes the controls can be actually quite limited, yeah. But very much so. And by the way, since we're talking about this, time course designs are really good designs if you can access this type of data, because remember we talked about blocking, right? We can eliminate some of the variation by combining measurements within the same block. Well, in time course, a person is a block. So if you compare these two groups, so you compare healthy versus disease, but you have some variation person to person and some variation person to person, and they're not the same people, right? So your variation is inflated by person-to-person variation. But if you have a time course design, then each person is a block, and you can compare the differences between time within the same person, and you eliminate person-to-person variation. So this becomes much more effective when this type of designs are accessible, if they are analyzed correctly. Okay, so the next step here's okay. So we parsed experimental design. We know what type of comparisons we want to make. So the next step is quality control. So there is actually a wide variety of things that should be done as part of quality control. So we will take it in a very narrow way here, and we will say, okay, let's look at the data in our experiment. So this is the mass spectrometry runs. This is the log intensity, and the boxes here highlight log intensities of every single peak measured on this experiment. Multiple proteins and whatever you have, all endogenous, right? So, and we see something like that. So, what's going on here, right? So, well, we know, right? So the line in the middle is the median of all the data points, right? The colored boxes, they're 50% of all the data points. So we see the systematic jump halfway through. And so is it the biology, or is it the artifact of data collection? And the fact is that it can be both, right? And oftentimes it's hard to tell. So in this particular case, it was actually nice because it was actually a SRM experiment with labeled reference peptides spiked for each endogenous peptide. And so now we can actually look at both panels. So these are the references and these are the endogenous. And we know that the references are supposed to be constant. It's not always possible because we may not necessarily spike it exactly in the same concentration and so on, but that's the intention, right? And so we see that the references, even though they're not identical, they're much more stable than this, right? So this points to the fact that this actually reflects some biology, right? And in fact, from what we know about the experiment, so it was a SRM experiment of yeast samples which were subject to stress, and the measurements were acquired on proteins which were supposed to respond to the stress. And it was a fairly limited number of proteins, so clearly some of the proteins became upregulated with time. And so this will help us to see how we can correct for some of the differences which occur at the reference stage without overcorrecting for the changes in the endogenous peptides. And so this would be the example of what MSstats would do. So we would use quantile normalization to equalize exactly all the reference boxes, and whatever changes applied to run 1 here will be transferred and applied exactly the same way to run 1 on the endogenous set. And you see now that it corrected a little bit without overcorrecting the differences. So let me spend a little bit of time on normalization, because this is actually a really, really important part, you know. So we often tend to kind of spend a lot of time on statistical models and so on, but the data that goes into the models is really important, and that's what will determine if we can actually be successful or not. So this is another experiment, which is actually a dilution experiment. So it's terrible the way it looks. I hope you can see at least a little bit. You have the slides on GitHub, right? So you can just look on your screen as well. Okay, so here is the MS1, MS1. This is the log intensity. I have really nice on my screen. Okay, and so you see that the boxes kind of increase with the rounds, right? And it is expected because we know that it was a titration experiment. So, but let's pretend we don't know it, right? Let's pretend that all we have is label-free experiment, and we have the data that work like that. And so what do? Is this a systematic shift due to the technology, or is it something which is maybe biology, right? How do we know? So, for example, if we decide that this is primarily due to the technology, one way to normalize this is to equalize the centers of the boxes or equalize the boxes entirely. So if we equalize the center of the boxes, well, you see that we removed all the effect of the dilution, right? So essentially we threw away the baby with the bathwater, right? So we try to correct for whatever technological artifacts, and we remove all the actually relevant quantitative signal from this data. So it's not a good idea to do it. If we do have labeled references, which we actually had in this case, equalizing the references really allows us to keep the biological signal, but just correct for some technological artifacts. And so the design of normalization is really a very important thing, which we need to think through as part of the design before collecting the data. And so let me just kind of work in a little bit more detail through 3 most common normalizations that we use in MSstats. So the first normalization is based on the standard. So let's say we have a protein in the mixture, which we know is supposed to be constant across all conditions. So if we have such a protein, so we essentially have a 2-step algorithm. So we subtract from every feature the median of log of each intensities of the standard, and then we add back the median of all the medians in the round, just so that our values are back on the original, in the original range. So essentially what we are doing is we're just equalizing so if we have one protein standard, let's say it has 3 features, so we'll take the median of the 3 features in run 1, the median of 3 features in run 2, the median of 3 features in run 3, and then we equalize the medians between the run, and we apply the same shifts to every endogenous protein. Right. So that's what we're doing with this algorithm. Does it make sense?
Is this for synthetic protein or peptide like this, or can you?
Very good question. And the answer is it depends. And so this kind of goes to my pros and cons associated with that. So let's see. First, let me just, I'll get back to this in a second. So let's just say what are the good things about that. So we know that the standard, if we spike some kind of synthetic standard, right? We know it doesn't have biological variation, right? So this is good. And it doesn't matter if we have a lot of features in the experiment, few features, well, it's always the same standard, right? So now the problems are, so for example, here, if we spike a synthetic standard, so we can only account for whatever problem happens after we spike the standard, right? And usually a lot of these kind of artifacts occur not at the mass spectrometry stage, but much earlier, right? So how the samples were stored, how they were collected, you know, how many like freeze thaw cycle, right? Enrichment. So Ideally, you would have a standard very much upstream, right, which would actually account for all of that. And that's much more difficult, right? So some people say, well, how about the endogenous protein standard, which we know is not regulated at all. So from what I hear, no such protein exists, right? That we know no matter what we do to the sample, it's always constant, right? I don't know, maybe you know of one. I've never seen. So it's tricky, right? So it's actually finding a standard which really reflects everything you want. Plus, if we spike synthetic standards, you have to really have a good hand, right? And make sure it's constant, right? So there are all of these challenges that you need to deal with. So this is on the kind of experimental side, but there is also on the statistical side. So imagine now that you have just the standard which produces one peak. And let's say this peak has an overlap or some kind of, you cannot quantify it accurately. So now you're normalizing your data with something which is noisy. You'll actually introduce more noise than correct for the noise. So the standards are not so easy. So the best practice that I've seen so far is to have multiple standards and which control for multiple steps. And ideally, you would have a pair of standards so that you can one standard for normalization and the other standard for verification. So you would only use one standard to apply this algorithm, and then you have the second protein to see, okay, did I make it better or worse? If the second protein became worse, then you have reasons to think that your standard was not very good, right? So this kind of, it's a compromise, but it's a reasonable compromise.
Has anyone looked at variance stabilization for normalization?
Very much so. Okay, let me finish this and I will get back to this. I omitted this for a reason, so maybe I could.
I was just asking because that's what I used when I was doing microarrays.
Yeah, I know. It's very popular in microarrays. This is the one that I don't like because it leads to overfitting very easily. It has many parameters and it can overfit your data. So it's useful for certain downstream analysis, but not for the type of things that we want to do here. So my attitude here is to normalize as little as possible, because you can really easily, over manipulate your data. And so I'll give you some example in a minute. So median normalization. So the standards are good because they can be used regardless of how many features you have. So for example, if you have targeted experiments, usually you would be in a situation like that where you have many things change because, well, you target these proteins for a reason, right? Because they may be involved, right? So the standards are really the best way to go. Now, another very popular approach, which we use for label-free experiments, is median normalization. So it's also constant normalization, so which has a very similar algorithm as before, except that before we had 3 features of a protein standard, we take the median. Now we take the median of all the endogenous features in the run. And we do it if we don't have a standard, right? So now what we do, we take run 1, we look at all the endogenous features, find the median. We take run 2, all the endogenous features, find the median. Run 3, and then we equalize the median, right? And apply the same shifted medians to every other intensity in the run. And so this would look like that, right? So this is a bad example, but it's still an example, right? So here, obviously, the medians are not the same, and we would equalize the medians. So the rest of the boxes doesn't have to be identical, but the middle line is identical. And so the assumptions here are that the majority of endogenous proteins are not affected by the condition. So we'll say, okay, between one condition and another, maybe some proteins vary, but the median abundance across all the runs stays the same. So this is particularly useful when you have label-free DIA experiments, which have thousands of proteins, or maybe shotgun experiments with a large number of proteins. So the advantages are that the median of all the endogenous features in the run is much more stable than the median of the 3 features of a standard, right? So it's much less likely that you'd introduce the noise by this type of normalization. But the disadvantage is, of course, that if you have many features changing, like here, then you would actually remove the signal. So I would say that using standards is really important in targeted and confirmatory studies, and median normalization is useful if you have label-free but very large discovery experiments where you can assume that the majority of things do not change. And the last type of normalization, which also was developed from genomics, by the way, quantile normalization, Raffaele Rizzari was the person who proposed that, so you can ask him about this type of things tomorrow as well. So essentially, it assumes that not only the median of the endogenous intensity is equal, but every other aspect of the distribution. So it would actually equalize the full boxes around the median in addition to the straight line. So what essentially you do is, well, that's the actual algorithm how you do it, but the idea is that you just equalize not only the median, but the 10th quantile, 15th quantile, 20th quantile. Very much so, and that's exactly what I'm saying here, right? So it is extremely aggressive.
It seems like it's removing too much of the biological variability. Okay.
Exactly, and this is why we don't recommend using quantile normalization on the endogenous, but we use it if you have multiple standards. And this can be more interesting because standards don't have biological variation, right? And so, in particular, what MSstats does is if you have experiments with labeled references, so you pretty much have as many standards, reference standards, as endogenous proteins. So it's actually quite a few numbers in each box. So then it may be more meaningful to equalize all the quantiles and apply the same shift everywhere. Yeah, so we would not recommend quantile normalization on the endogenous features. Well, all data are biological, right? So let me review. So if you have many proteins and many features, endogenous, no labeled reference, constant normalization with the median. If you have a small-scale experiment with a few features, standard is probably your best option. And so you can have a single standard and then you would equalize that, or ideally you will have many standards and then you can use quantile normalization on the standards and do that. So your choice of normalization will depend very much on what type of experiment it is, how many features you have, and how many of those features are actually changing.
Define many versus few features.
Well, so I would say, it's actually, you're right, it's not necessarily the number, but more like a proportion of changes. So I would say that if you expect 10% of your proteins changing, you can use constant normalization. If it's more like 20 and 30% of things changing, it's getting already in the danger zone. If it's more than 50% of proteins changing, then you really don't want to do endogenous normalization. And so in targeted experiments, the usual order of magnitude is like a few hundred proteins, right? And those are usually targeted like specifically target a pathway, right? Or you target some things which you pre-screen. So in SRM experiments, it's very likely that more than half of the proteins are regulated. So I would not use anything based on endogenous intensities for normalization because you targeted these proteins because you expect them to be changing, right? On the other hand, you have a DIA experiment where you can pretty much quantify everything, right? And maybe many proteins change, but you can probably quantify a lot more of other proteins. So then using the median normalization is a better way to go. And you can still have a single standard, like for reasons we just discussed. So especially in DIA, when you have too many peaks, so your standard can be compromised with overlap with other peaks. So the standard can be a bit tricky to use.
So for the quantile, the problem is that maybe you miss many things if you do the quantile.
No, it's really overcorrecting quite a bit. So see, it really assumes that everything is equal, including like the maximum, right, and so on.
Yeah,
so if you have, in one of the conditions, the protein was like very much upregulated, right? Quantile normalization brings it back, which is kind of silly, right? That's not what you want to do. So constant normalization will adjust it up and down based on the median, but it will not require it coming back completely. So especially in the extreme changes, quantile normalization really reduces that. No, it's more like based on your experimental design. So if you have an SRM experiment, you know many things will change. You would not want to do endogenous normalization because you can't really test that because how do you know? It's like here, so I can do a statistical test, and the test will tell me there's a trend, but it will not tell me if this trend is biology or technology. The test will only tell me there is a trend. And if it's a good idea to normalize it out or not, it's not really math, it's more like the design behind that, right? And say, what is the most likely cause of this trend? If this likely cause of this trend is technology, because we don't expect biology to vary that much, then you can equalize medians. If the more likely trend is biology, because it's a targeted experiment and you're really focused on proteins that do change, then you probably don't want to remove that. So, the numbers can only tell you there's a trend, but they will not tell you why.
Well, it's more like if you have two groups and you anticipate there might be a global shift in the
But but again, global shift can mean different things,
Yeah.
right? Because if we have 10,000 proteins, do you really think the 10,000 proteins change between two conditions?
No, but a subset might because of information.
But right, okay. So now, if you think that this subset is half,
Yeah.
then you really need a standard, right? If you think that this subset is 10%,
Yeah.
then you can use.
Okay.
So that's what I mean,
Yeah,
right?
yeah.
I think there was a question.
So do you use median for large data sets also, just because of convenience, because you use it for small data sets as well? Because maybe it's more robust for small data sets, but if you have really large data sets, median and mean.
Actually, we use median normalization primarily for large data sets, but we would not use it for small data sets. So I was kind of trying to summarize it. Maybe I should have put it on the same slide. So for standard-based normalization, so use multiple standards and best use with targeted experiments, right? Or even with large-scale genome-wide experiments, if you can have a reliable standard. So development of the standard is kind of an extra issue here, right? So now median normalization. So this is the experiment with many features, and by many, I guess I mean shotgun LCMS or DIE. So it means that only like 10% or so will be varying, right? And then quanta normalization, it is really very aggressive, so you don't want to apply it to endogenous features at all, so you primarily apply it if you have multiple standards. And then you transfer the shifts in the standards to the endogenous. Does it answer the question?
Well, yeah, I was more like interested in mean versus median.
Oh, that. Yeah, so the mean will be more affected by a single outlier. Oh, yeah, of course. So median is much more robust to single protein, which can be jumping up and down. So the center of the distribution will be much more stable. Yeah, so we don't use the mean.
In a large data set, it shouldn't matter that much, right?
If the distribution is symmetric. If the distribution is very skewed, for example, you have many proteins which have very large values, but you have then the other proteins are very concentrated in one area, then the median will be smaller than the mean. So it's not really in the numbers. So if you have a pattern which looks like that, and remember we talked about this last week, that we can compare mean to median as a measure of skewness, right? So the mean will be here, but the median will be here. And it doesn't matter how many data points you have. So your box plot would look like this. And we actually have these examples here, I think. Yeah, you have some box plots here which are very skewed, right? So the mean will be very much affected. So it doesn't matter how many data points, it's more like what is the skewness of the distribution. Wait, I think you had this.
I'm just trying to ask a question in shutdown proteomics. Assuming that the difference between all the proteins between two conditions don't, like the number of proteins don't differ too much, is low
So once again, the difference in abundance is low, right? Or the numbers of proteins.
the number of protein that differs between two conditions.
Okay, it's small.
Is small. And because I've been using coefficient of variation for each, let's say, protein to see between conditions, just to get assessment of how different, so that the variation between all the proteins. Is that a possible way of assessing how normalization is? Because you would get a distribution of coefficient of variation. So
Not really, because I can normalize every value to the same number, and I will have coefficient of variation of 0. But it doesn't mean that it's a good normalization, right? So not really, because you can totally overcorrect the true variation, and it will look like, oh yeah, it's very stable. So what you can do is to look at coefficient of variation separately within each group and things like that. But again, your normalization can overcorrect some of the changes as well. So our approach is to do as little to the data as possible. So it is true that CVs are used often just to see how precise the measurements is and how reproducible the measurement is, and it's a good thing, right? But it doesn't have the concept of the true biological variation behind that, and so it's a little bit arbitrary, these cutoffs, right? So what we advocate more is understand what type of assumptions we actually make, right? So if we normalize with a standard, the assumption is that the standard doesn't change. If we normalize with the median, the assumption is that the majority of the endogenous features don't change, right? If we normalize with the quantile, we assume that the whole distribution did not change. And so these are clear assumptions. So the danger with CV is that I can have one method and I have a CV, I have another method, I have a CV, but it's not immediately clear what the assumptions are. And if you do not state your assumptions clearly, you cannot evaluate if those assumptions are plausible. And so this is something which is underappreciated with normalization, that it's essentially there's like a statistical model behind that. And it is really important to spell out exactly the assumption, because next thing you do is to say, is this assumption plausible for my particular experiment or not? And you can kind of put CV as part of this, but it's really important to understand what was the assumption behind that. Ooh, okay, let's go back. Can you speak up?
So it's regarding the usage of the term single versus multiple standards. So when you spike in IRT to your target experiment, is that considered multiple standards? And does it qualify for you to use the quantile normalization?
You could, provided that your IRT peptides are spiked in the same concentration. We actually had recently a situation where, so I don't know if you know, IRT peptides are used to calibrate retention time because they appear in specific places in chromatography, and so that's their primary use. Now, you can have a secondary use of them by equalizing the intensities. So they're not using them in the retention time space, but in the intensity space, provided that you spike them in the same concentration in every run. So we recently had a situation where, for some reason, they didn't spike them in the same concentration. So then you can still use them to calibrate your retention time, but you cannot use them anymore to calibrate your abundances. So it is possible, because it's like any other standard pretty much, but then you have to be careful that you spiked at constant concentration. And again, you remember that it only accounts for technological shifts which occur after you spike in. So it still doesn't help you with all the upstream effects.
So when you mean standards, do you mean internal standards, like some proteins that you choose?
That's exactly the discussion we just had. So it can be essentially any protein which you know does not change biologically. And it can be because you spiked a analyte in a constant concentration, or because it can be a protein which is regulated so tightly that it would not shift. And so what we just said is that endogenous, protein, you never know if it's not affected by a stress. However, you may come up in your specific biological system. You know about your stresses so much that you can safely say that this protein will not be affected. But then you can use it as an internal standard. But it's not a very general strategy. So again, unfortunately, there's no single recipe to do it well all the time. IRT peptides are a good thing if you can spike them at constant concentration and you're kind of mindful of the fact that they don't account of the upstream effects. Endogenous proteins that don't change, this will be perfect if you have them.
So if we spike in equal concentration, can we still go ahead and use the quantile normalization?
Yes, but it depends how many IRT peptides you have and how many features per IRT peptide you have. So, but you can do quantile normalization with 3 features if you want, right? So you will look at the median and the maximum and the mid. But it is true that quantile normalization works best if you have a little bit more features, right? But indeed, if you have multiple features, you can do exactly that. I think there was another question somewhere. No? Pick up? Okay, but it's a really good discussion, and I think Meena will spend time on that as well, talking about how to handle that. Okay, so that's what we do here. So now I'm in trouble because we're running late, but I'll do my best to finish, and maybe we'll see. Okay, so statistical modeling. So this is now what happens once we actually read the data to MSstats, so log, transform, and normalize, right? So the next thing. And the next thing is to actually represent all the complexity of the data. If I go back to this figure, so we have, for one protein, we have multiple features, multiple conditions, multiple runs, and missing data, right? Or somehow low confidence values. So how do we handle that? And so everything I will talk about next is about one protein primarily, but you can just imagine that we just iterate over every protein one by one in the data set. Okay, so if you were here last week, you remember that we talked about the fact that we can extend two-group comparisons by t-test for more complex situations. And so this was one of the slides that I showed. So here's, for example, multiple groups. And so each group has its own mean. So here, y-axis is log protein abundance. The dots are biological replicates in the group. And so we are looking at different means in each group, but we assume that there are some shared patterns and variation around the mean. And so we can extend the two-group comparison to a model which will say the observed feature log intensity here has contributions of the disease group. So the protein can be more or less abundant depending on from which group this value came. Then there's also a deviation due to the subject, just one person from one person to another, there's a natural variation of protein abundance. And then we have some random deviations of measurement error. So these models are very general, so we can also work here as an example where we have the biological and technical replicates. We can also extend the same type of models to cases with biological and technical variants. So these are very general models that are called linear mixed models, which can reflect very complex combinations of conditions and so on. So it would require like a lot more time to go over that, but I just wanted to kind of highlight the fact that we use this kind of more general family of linear mixed effects models to reflect these data structures. And so I will not do much math. I just want you to kind of have the keywords behind it, right? And the good news is that MSstats does all of this behind the scenes. You don't need to worry about that. But just so you know what's going on, we take this table for one protein, and we partition this into two components. One is the yellow component, and the other is the pink component. So the yellow component reflects primarily the measurement technology, right? So the fact that mass spectrometry gives us multiple features, and these features have some missing values and noise and so on. The pink component reflects the biology. So this is multiple conditions, multiple subjects within conditions, and so on. And so we can write a linear mixed effects model which kind of specifies the contributions from the pink sources and the contributions from the yellow sources. And so just like I did this previously, saying, well, there are different contributions which affect the log intensity of the feature. So we can extend this the same way, and we say we have all of the biological contributions and technological contributions which affect the log abundance of the feature. And so in statistical language, this type of approach has a very specific name. So it's called a split plot design. And split plot means that all the features acquired in the same run share the technological properties of the run. Then here, the set of features from the same run, they share technological properties of the run. And then we have to work across all the runs. And so what this means kind of statistically is that we will decompose this model into two pieces, and we will first summarize all the intensities across all the features to obtain one number per protein per run. And then we will use a linear model to look for differences between protein abundances on the summarized protein levels. And so this is very useful because on one hand, we actually have some numbers. We can say this is the estimate of protein abundance in a person, summarized across all the features after normalization and so on. So for example, if you want to do clustering or classification or draw heat maps or things like that, you can use that. Or we can do the next step and just focus on the pink part of this diagram and essentially use our t-test if we have two groups or extend this to other models. So that's really what's going on. So we will have two steps. One is where we focus on the yellow part, and we will do the summarization, which accounts for missing values and so on. And the second step will work on the biologicals. So, but before we do that, we need to consider missing values. And so this is something which we found is quite important for us. So we need to find a way to handle missing values. And this is really important because missing values can occur for multiple reasons, right? They can occur because we have peaks which are so overlapped that we cannot quantify individual peaks reliably. So we just say we can get the number, or we can have missing values because the analyte was below the limit of detection. In which case, we don't have the number, but it's not arbitrary. We know that it has to be low, right? So it's not just any possible number. And so we need to distinguish this. And to make things more complicated, the patterns of missing values or low values or some unreliable values is very specific to the data processing tools. So if you quantify the peak abundances with Skyline, you may get different numbers than if you do it with OpenMS. Because different data processing tools, they make different decisions. Well, for good reasons, they optimize for different things. But the fact is that when we have really nice, abundant peak, most tools will agree. When the peaks are overlapped, low abundant, close to the noise, different tools may make different decisions. And so this is a data processing step which Meena has developed, and we found this really necessary and also useful to make it inclusive so that we can actually work with different data processing tools. So this is an example of how it works. So let's see, these three figures, they come from a single shotgun label-free data set. If you are familiar, it's the LFQ paper by Jürgen Cox and Matthias Mann and others. And this is a data-independent acquisition data set, which is also label-free, but it works with SWAT. So now here is the same data set processed with Skyline, MaxQuant, and Progenesis. And here is the same data set processed with Skyline and Spectronaut, which specializes in DIE. The gray areas, they are log intensities of all the peaks across all proteins and all runs, everything in this data set together. And so notice here, the bars here reflect the number of zeros or very low values reported by these tools. And so again, same data set, right? So we're just looking at the same data set with different data processing tools. And you see, for example, that Skyline has 203,000 peaks. MaxQuant has 224,000, sorry, peaks. And then Progenesis has only 56,000 peaks, right? So it's like an order of magnitude less than here and here, right? So now you also notice that MaxQuant doesn't have any zeros, and Skyline has zeros, and Progenesis has even more zeros. You can also notice, like in terms of missing values, so Skyline has 33 miss NAs, and MaxQuant has 38,000 NAs, right? And so quite a bit of difference, right, in terms of their quantification. Also, if you look at the location of these gray areas, you see they're not identical, right? So they kind of shift some. For example, here Progenesis tends to have lower values than MaxQuant. Well, the shift itself doesn't really matter because remember we're looking for relative quantification. We compare differences. So as long as the difference is in the right direction, we're fine, right? So the absolute values don't really matter. But still, it's interesting to see that there is so much difference between data processing tools. And of course, here as well, right? So you can see quite a bit of shift, right? And also the the difference. So here you have 2,500 NAs, here you have 13 NAs, right? And so more zeros here than here. Again, it's not a judgment call. We're not saying which software is doing better or others. We just point out that we may have to handle different inputs differently.
Yeah, I've been playing around a little bit with parameters in different software, and that affects the missing.
Oh, very much so.
Too, so it's
Very much so. And so that's why I was showing this ABRF dataset in the beginning, right? So there are so many steps that you take, and if you know how to kind of mitigate these consequences, you are fine, right? But it is also easy to kind of go in the wrong direction. So this is what we do, because we really try to be inclusive and make sure that we can work with different tools. Yeah.
Are you estimating how much is censored, how much is missing, or is that something that?
We do, but not yet.
Okay,
So,
but I was just wondering, that's what those numbers are.
and that will, yes. So, well, it's actually a difficult question because it's not always easy to know. For example, we work very closely with Skyline, and we know exactly the convention with Skyline. So Skyline will report NA, and so you see here that they only have 33 NAs here. So Skyline will report NA only if it's a very highly overlapped peak. So they will not report NA otherwise. If it's a very low abundant analyte, they will find some low number. And you see that you have quite a few zeros here, and then you also have, it's hard to see, but there's like a tail here as well. So Skyline, and we know with Skyline that if it's an A, it means it's random. If it's low value, it's censored. But some other tools, it's not always possible to know exactly what's going on. And that's kind of the point. So what we decided to do, essentially, is to work with this type of figures and say that whatever low value is below some point, essentially we don't trust it. Call it 0, NA, missing value, whatever you want to call it. If it's low enough, we will not use it. And by low enough, it's actually indicated by this vertical dashed line. And so what we do is we find I think 99 percentile on the right-hand side. Then we find the median and we flip around the median so that we assume that the distribution should be roughly symmetric. And so we estimate a percentile of this distribution based on the right tail, and we use the mirror image. So essentially we have a somewhat empirical cutoff, which tells us that below this cutoff, we don't trust the values. And so unless the tool tells us that there's a difference between censored and missing at random, we will always assume that it is censored because it is more common, essentially. So here, for example, that 33 NAs, we will leave them NA because we know that it's not censored. But everything else, so every value below the cutoff, we will assume that it's low abundant analytes, and the numbers we do not trust. So that's the idea. So now, yes, just pick up. Sorry? So, that's hard to tell. So in Skyline, they're not, for the reasons I just explained, right? So NA means overlapped peak, 0 means low abundant peak. But in other tools, it's not always documented, so it's really hard to know. So if somebody tells us, we're happy to take it into account, but sometimes it's really difficult. And, by the way, versions of the tools change, and these things kind of evolve. It can also be somewhat of a moving target. What's called 0, what's called NA. So, for example, MaxQuant, it's pretty easy. You have zeros, right? So everything is NA, right? So it means that it's a mixture, right, of censored and overlapped or something like that. But because we have no other information and because censored is more likely, we'll just assume everything being censored. Yeah. But it's true that, for example, Progenesis has, Progenesis actually has 0 NAs, so all the zeros, right? But you have some others, for example, the Spectronaut, it has 13 NAs and 38,000 zeros. So, so for Spectronaut, I think it may just be an artifact of how the output is structured. Well, again, so we work, so first of all, we don't do imputation, not like that. I haven't told you yet what we do. But essentially, we distinguish two situations: when something is below the limit of detection and something is missing at random because we just cannot get the number. So if something is missing at random, we will not touch it. We will leave it NA. The problem is that for many tools, there is no such distinction. So if we cannot get to this distinction from the data set, then we will assume that it's censored. And we will work with this as if it's low abundance. If it's missing at random, we will never ever do anything with that. Okay, so we only do something if it's censored. And maybe one last thing is that one place where we don't do anything usually is in experiments which have labeled reference peptides. So if you have labeled references, we assume that it's unlikely that it will be censored, because if you spike references, you will probably spike them in enough concentration to actually see the peak. So if it is missing value here, it's more likely that it will be missing for some other reason than low concentration. So we would not do anything with labeled references either. But for endogenous, so if someone tells us that the reason was other than low concentration, we will leave it alone. Otherwise, we will assume that the missing was due to low concentration. Okay?
So both zeros and an ace are considered as low value.
For lack of more information. And I can tell you actually where they come from. So remember at the very beginning, I talked about these two representations, the wide format and the long format, right? So we actually work with this format conceptually, but this is the format we use technically in R, right? So what happens is that some file formats don't have this wide format, and so they will essentially output it directly in the long format. And so what can happen is that they can just forget one run. And for this particular protein, you will have no information in this run. So is it 0 on A? So then you just have to kind of fill in the blank yourself, right? And okay, let's call it an A, right? But it's probably because the protein was not found in this run. So it's probably still appropriate to think that it's censored, right? So, you know, as I say, you will see later, there's a wide variety of data processing tools that we work with. So it's really impossible to know for each tool what's going on. So we try to work as closely as we can with developers that we know, but there's limitation to what we can do with that. Okay, so this is actually what we do next. So the first thing, so remember we have two steps, right? So first we take care of the yellow part, which is the technology, right? We summarize, and then we take care of the pink part, which is the biology. So for the technology part, so first thing we need to do is to work with those NAs, which we assume are censored. And it is actually relatively easy to do because this type of censoring information is very common in other areas of statistics. So imagine, for example, that you're running a clinical trial and you follow up somebody in time and you look for survival, for example, right? And so you kind of have a person following the person for 10 years and then the person drops out of the study. So you actually never know how long the survival was, right? But the fact that the person dropped out of the study doesn't mean that it's a bad information, because you know that the person survived at least for that long. So you know that the survival was long enough. And so you can model this type of information statistically. So technically, this type of approach called accelerated failure time model is just a technical kind of term. But essentially what happens is that we take this yellow part and we say that each feature here has a combination from the features. Some features have higher ionization efficiency than others. There's also run. So some runs have more protein than others for whatever reason. And if we have this type of missing values, we would assume that they're missing because they are below the limit of detection. And so now what we can do is to essentially characterize the overall level for each feature, characterize the overall level for each run in a way which is not affected by missing values. And then we can impute the values here which come from this censoring type of estimation. And so the last thing we will do, we will use Tukey median polish, which is a robust summarization of this two-way table to have one number per protein per run. So I'm kind of hand-waving here a little bit. So Tukey median polish is essentially a robust alternative of two-way analysis of variance. if you have done any work with genomic data sets, you're familiar with, what was the name of the normalization? So the normalization for Affymetrix microarrays, they also use Tukey median polish to summarize multiple probes in one number. I forgot the name of the normalization. But anyhow, so just to review once again, so first we characterize the features and the rounds in a way which accounts for the fact that missing values come from below the limit of detection. Then we predict what these values would have been if we would have observed them. And then we use robust summarization to also remove the effects of outliers. Because in addition to missing values, we also have outliers which come from various reasons. So the first step takes care of the missing values. The second step takes care of the outliers. And so now what we have at the end, we have one number per protein per run. And so now this is the summary data set where we can just use this to draw heat maps or things like that. Or we use the next step to now work with the Sphinx side where we have one number per protein per run. And we can now do a t-test if it's a simple two-group comparison, or build more complicated linear mixed models if it's multiple conditions and multiple types of replicas. Okay, so then we need to do model-based conclusions and experimental design, but I'm running out of time, so I think now it's time for break for us. So during the break, I will talk to Meena to see if we can find time for me to finish this at some other point. So I want to make sure that you know as much as possible about these methods, because the next thing we will do is to use the ABRF dataset we introduced in the very beginning to essentially work through the whole process. And if I understand, we will even have a chance to experiment with different types of data processing tools as well.